This is 21.2, Applications of the Electric Field. This wraps up our chapter. Today we are going to talk about calculating the potential difference and calculating the capacitance of a capacitor. So our first part is the electric potential difference. Now there's two things that go with this. One of them is the electric potential energy, and the other is the electric potential difference. So electric potential by itself, before we start talking about difference or energy, electric potential is just an area of charge. So let's say over here we have a whole bunch of negative charge. And then over here we have maybe some positive charges or a zero charge or something. And that's electric potential, it's just the area. So this is area of charge. Then we have electric potential difference. And difference is when you're comparing one thing to another. Right? So we call it delta V. So electric potential by itself is V. Electric potential difference is delta V. And that is this one compared to that one. So these negatives and these positive charges are going to attract each other. So there's some charge over here and some charge over here. There are different charges, and that is going to cause electrons to flow to make them even or neutral as much as they can. And then the last little bit that we have is electric potential energy. And energy is either just energy in general, mostly work. Let's get rid of this E, because that's going to confuse it when we start talking about the electric field. It's just work. And it's measured in joules. And we've already talked about energy. We've talked about potential energy, as in gravitational potential energy. So if I lift this calculator up here, now that it has some sort of height, I've stored it as gravitational potential energy. I did work on it. I transferred my golden grams from this morning into the calculator. So now it's stored potential energy. And that, when I drop it, it's going to turn that potential energy into kinetic energy until it has no energy down here. So it's transferred into kinetic energy. Same thing with electric potential energy. If you have a positive charge here and you drag a negative charge this way, we've added energy to it. We've done work on it to pull it away. So now that it's over here at this spot, it has stored potential energy. So when we let it go, it's going to turn that potential energy into kinetic energy as it moves closer to the positive charge. So electric potential is all talking about charges. The electric potential, as in the area, is just talking about the charge on that area. Electric potential difference is the difference between two areas of charge. And electric potential energy is the amount of energy that these charges have stored in them, and when you let them go, something's going to happen. They'll either move towards each other or move away from each other to release that energy. So stored energy, difference in charge, actual area of charge. So they all sound the same, but they're talking about different things. So we have one equation up here. We have the potential difference, delta V, is going to be equal to the energy or the work, the electric potential, this stored energy, divided by the charge. see any cups out, so I'm assuming it's all finished. Here is a little picture for that gravitational pull for electric potential energy. Over here, this would be gravitational. We do work on an object and we lift it up, so now it's gained gravitational potential energy, and we let it go. That potential energy will turn into kinetic energy. The same thing happens with charge. If we pull these charges apart, we're going to put work into it. It'll be stored up here until we let it go, and then that charge is going to flow towards the electron. The only difference is with electricity, or with electric charges, this charge, if they were both positive, would move it away. Whereas gravitation is always an attractive force. With electricity, we can have both attractive and repulsion. Here's another picture talking about the same thing that we just did, so we'll skip it. It's not that exciting. Don't forget that energy, this work, is FD cosine theta. And for pretty much everything in your homework, F and D are in the same direction, so the angle is 0, so your cosine theta just goes to 1, so you don't even need to write cosine theta, unless it gives you some sort of angle, and then you can put it in. But if it doesn't give you the angle, which I don't think any of them do, you can just leave the cosine theta out, because it crosses out. It turns into a 1. Okay, electric potential difference in a uniform field. So far we've only talked about one type of field. We've talked about the electric field around a single charge. We'll call it a positive charge. So the electric field, as it moves away from this charge, it spreads out over a larger area. So the area here is very high, and the area over here is going to be lower. And as you move away from that charge, you get less and less of a field because it's further away. You feel less force. So a uniform field can be created by using plates. And they call this a parallel plate capacitor, where one side's negative and one side is positive. And the best way to do this is to hook it up to a battery. So this is your battery. We have the negative side, we have the positive side, and the electrons march along here and store up on this plate until they get so big, there's so much charge, that the electrons snap over to the other side. And this movement, well, it's not actually the movement itself that creates the electric field, well, a little bit. The electrons move a little bit, and that creates the electric field. So you end up with a uniform field across it. So if we look at this field up here, at this point it might be 4, and this point it might be 3, and then as you move out it's 1. So 4, 3, 2, 1. As you get further away, the field gets less and less. But here, it's 4 all the way through. And actually it would be 4 up here, and 4 over here, and 4 over here, and 4 over here. And as it moves, it's going to go to 3, 2, 1. So as it moves away from the parallel plate capacitor this way, it gets less. And same thing on this side. It would be 4 on this side. And as you move away, the electric field will get weaker and weaker and weaker. But this area right here gives us a nice uniform electric field. And when we have this nice uniform electric field, we have another equation that we can use to find potential difference. And that is the electric field, the uniform electric field, multiplied by the distance between those two plates. Make sure you put this in meters. Okay, now that we know what a parallel plate capacitor is, and it's just as it sounds, two metal plates hooked up to a battery, we can talk about how they found the charge of an electron. Now, electrons are super duper duper tiny, right? So it makes it really hard for us to look at them, and let alone find what their charge is. Well, in 1909, a scientist, obviously his last name is Millikan, was able to take oil, which has its own charge, and he atomized the oil inside of this container. And then the oil condensed into a single droplet, which he was able to figure out its mass and thus its weight. So he knew how much force, the gravitational force was to pull this drop down. When it dropped between the two parallel plate capacitors, so two metal plates that are charged, he could change the amount of electric field in between these two things by using the battery. So you could turn it up or turn it down, and that changed the electric field. So at some point, you can turn the electric field up so that this force of the gravity is counteracted with the electric field, so it would hover in the middle. So he had electric force up. So here's your droplet, right? And you have your electric force pushing up and the weight of the thing going down. So at some point it would hover, it would balance. So he knew the electric field, and he could find the mass of this. And then if he turned the electric field up, the droplet would accelerate upwards. So he could find the velocity and the acceleration of that drop upwards. And then if he turned it down, then the gravitational force would be winning, and it would accelerate and move downwards. So by calculating how fast this happened and the electric field at the same time, he could calculate the charge on the object, on the drop. And here is the equation that does that. So this is our last equation today. I know I've thrown a lot of equations at you today. And this is the capacitance of a capacitor. Now, a capacitor is a thing that stores electric charge. So this parallel plate capacitor, what we talked about here, it just looks like metal plate with positive charge on one side and negative charge on the other. It has some distance between the two plates, and it's hooked up to an electric potential difference, so like a battery. And these electrons, they march along, and this would be the positive side. And the electrons, they march along, and they go, and they store up on one side. And when they get enough charge on them, they will move over to the negative side and then move along. And so you get this full circuit, and you get a stored up charge here on this plate. Now this is the simplest type of capacitor. There are lots of fancy capacitors. If you've ever opened up on your computer and you look at the cards in there and the motherboard, they have little things that look like that sticking up out of there, or maybe things that look more like a balloon sticking up. Those are capacitors. They store up charge. And when the computer needs it, they release that charge. So capacitance is measured in farads after its scientist. Your Q is the charge that it's holding. And then delta V is your potential difference in volts. Another big one that they use for capacitors, your camera flash, like on your phone. How it does a flash? You can hear it charge up a little bit, and then when you release it, you've released all this energy and you go all over it. So that's a capacitor as well. That's a very common one. Okay. Here's explaining that capacitor. Parallel plate stores charge. This is usually what they look like, just 2 plates like that. Now the electric field between parallel plates, you're going to have to draw this tomorrow in your lab. This is a representation of those plates here. So someone drew electric field lines for it just as a representation. They always go positive outward, so we can see the arrows going to the right on the right side and to the left on the left side. And they go towards the negative, so on this side they are going towards the negative, and it wraps around here. So in here you have a nice even field. Now remember that electric field lines, even though we draw them as representations, they really do exist. So this is 2 parallel plate capacitor, or a parallel plate capacitor, and some iron filings. And you can see the iron filings lining up with that electric field. And they're kind of curved around the edge here and curved there. And you can almost see them kind of this line. So they really do exist. We don't just draw them as representations, but they are real, but they're invisible. All right, and our practice for today. It says the electric field in a particle accelerator machine is 5 times 10 to the 5 newtons per coulomb. How much work is done to move a proton, and the proton, you're going to need that constant for your homework, 1.6 times 10 to the negative 19 coulombs. It is moved a distance of 20 centimeters through that field. So we have a lot of equations. This is a lot of new material, which we haven't worked with it too much yet. So reading through it might confuse you a little bit. Just stick to the units of the numbers. And then look at your equations. The conceptual stuff will come. So 5 times 10 to the 5 newtons per coulomb. What's this? Electric field. Good. And then we have, it's given us Q is 1.6 times 10 to the negative 19 coulombs. And we're also given 20 centimeters. What's this? Distance. Don't forget to turn it into SI units. What are we looking for? Work. Okay. Now, which equation do we need? Second one? Yep. Well, maybe. F times D. We don't have F, so that's not it. With these ones, a lot of the times you're going to have to use multiple equations. So you're actually going to use, oops, no, I did that wrong. Yesterday, or on the earlier one, it was like that. Okay, so we have E and D, and we need Q. So you're going to use this one right here and this one right here. Did that work? Yeah, to get work. Because we don't have force, and we don't have a way of finding force with this. If we look. So since they're both set equal to delta V, we can set them equal to each other. Work over Q equals ED, and solve for work EDQ. So you just multiply all of them together. So I set this one equal to this one because they're both equal to delta V. I got 1.6 times 10 to the negative 14. Somebody else get that? Questions? Okay, we're going to start with our clicker questions. The first one says, in an oil drop experiment, a drop with a weight of 1.9 times 10 to the negative 14 newtons was suspended motionless when the potential difference between the plates that were 63 millimeters apart were at 0.78 kilovolts. What was the charge on the drop? I'll help you set this one up, because I know you guys are new to a lot of these things. 1.9 times 10 to the negative 14 newtons. What's that? Newtons? Force. Then we have 63 millimeters. What's this? Distance. Make sure you convert. 0.063 meters. And then we have 0.78 kilovolts. What's this? Volts. Potential difference. That's the delta V. V goes with V. Volts goes with potential difference. Make sure you convert this. It'll be 780 volts. And what are you looking for? Charge. Q. Okay, so we need FD, V, and Q. FD, V, and Q. Okay, so you want this one and this one. So delta V equals work over Q. You can replace work with FD over Q. And then flip-flop the bottom and the top. Q equals FD over delta V. And I'll let you finish it from there.